So, bingo. Okay, let's put this on your shirt here. Belt or in your pocket.
Okay.
Okay. Well, thank you for inviting me, Jose Miguel. Well, I'm going to talk about my own experience with a protoplanetary nebula that we observed with TIMI-2 at the 3.6 and what we could do with CanariCam. So everything I'm going to talk about is based on this work. This was a paper published in 2006. And as I said, this is a protoplanetary nebula that saw pH emission plus other solid state emission. Well, I'm going to talk fast about why it's important to study protoplanetary nebula. So let me start from the AGB to PM planetary nebula evolution. The protoplanetary nebula is a very short phase where there are very few objects known, so we can call as a missing link between the asymptotic giant branch and the planetary nebula. At the tip of the AGB, the mass loss is of the order of 10 to the minus 4 solar masses per year, and the mass loss suddenly stops, and it takes something like 10,000 years to the central star to reach high enough temperature to ionize the gas. So I'm going to show you a movie of what should be the evolution from AGB to planetary nebulae, and post-AGB phase, which will form a planetary nebula phase, is just a very short time at the end of the movie. This is from this paper here. Oh, let's see. The AGB lasts something like 1 million years, and the strong mass loss just happened at the end of the AGB phase. Here we have just a very just 10 to the minus 6 solar masses per year mass loss, and when this red button sign is when we have the thermal pulses at the end of the AGB. We have 3 strong thermal. And now this last second is the whole planetary nebula phase, which is about 100,000 years, and the post-AGB is 1/10 of that. So this is a very short phase in the evolution of the star. We hardly could see here, but it's very important because this phase is going to say the PN morphology. So that's the rationale of studying this phase. These are some examples of planetary nebula. This is the Dumbbell planetary nebula, and what the halo that we see here is the AGB phase. So what we aim to study is when this AGB phase stops, so the planetary nebula, the nebula, because having started the ionization is just 100 years, something like that. This is the same in H2, and we see here the contrast between the planetary nebula, which is this part, and the AGB cell. Yeah, this is H2, so excitated H2. So, well, what are the characteristics of planetary nebula? They usually show a double peak emission in the set. So have a photometric, the central star has a peak in the optical range, and a strong infrared excess from the cold detached envelope with temperatures between 100 and 300 K. Well, as I said, there are different processes that different authors claim they may shape the different morphologies observed in planetary nebula, interaction of stellar winds, binary system as central star, non-radial pulsations, and also magnetic fields. So by studying this phase, we are studying the physical processes that will be critical to have different morphologies. So why we choose this object? Well, we choose this object because, of course, we have some information from ISO. Garcia Lario et al. Studied this object with SWS and LWS. It shows PAH and also strong features on 12.6 and 30.4, and also it shows strong 21, 26, and 30 micron features that it's not clear what caused this emission. There is several authors propose different molecules. And also from HST, it shows a multipolar structure. And as I said, all this has been published in this paper in 2006. So the observations were with TIMI-2 at the 3.6 telescope. Pixel size was well, I have to say this instrument is already decommissioned, but well, now it's available this year on the VLT. We have very good scene, 0.5 arcseconds, and we observed in the 8.6, 11.5, and 11.7 filters. We use the standard nodding chopping technique with a nodding chopping through of 15 arcseconds, and each image is a combination of 50 of 100 images with interaction time of 18 or 40 milliseconds, and the chopping frequency was 6 Hz, and the total the on-source interaction time were typically of 2 minutes. So those sources are very bright. We didn't need to interact, though, as Charlie was saying, I mean, on-source is not the real time you observe. So as I said, we have very good scene, and but the problem with the 3.6 is diffraction image at 8.5 microns. It was something like 0.6 arcseconds. So what we did is deconvolve using the Lucky-Richardson algorithm with point source, and this is an example of a point source. And after using the Lucky-Richardson algorithm, we obtain an image. Here the pixel size is 0.2, so we obtain an image of 0.4 arcseconds. So we could reconstruct the image from the diffraction effect. So in principle, if at the GTC you may have a scene of 0.1 arcsecond, you could try to use this technique. As a comparison, well, this is the comparison between raw images in the 3 filters and after the convolution. And as a comparison, I put here some images obtained by other group with T-Rex that was published late in the same year. Also, it's the same object. I mean, this is without any deconvolution. It's just the T-Rex. So, but we now, I mean, we published. This was almost 1 year. I mean, we published in February, and that came in November, December. So we didn't know about that, of course. But you see that the results is pretty much similar. So, of course, well, T-Rex is better. But you see that the convolution process was pretty good. Well, of course, from this image, it's clear that there is a torus around the central star. So now we just did a spatial cut in the direction of the torus, minus 10 degrees. And we can, this is from the 8.7, the 8.5, 11.9 filter. We see the profile is pretty similar, and this is dominated by pH emission. And the important thing is we can work out the dimension, the separation of the torus, or the dimensions of the torus, and we can infer a dynamical age from that torus, assuming a distance of 1.6 kiloparsec. This will correspond to 640 astronomical units. And we know the expansion velocity from CO. The CO is associated with this torus. It was 16 kilometers per second. So a dynamical age of 190 years was derived, which is consistent with what you will expect from a protoplanetary nebula. So that means the AGB phase stopped 190 years ago, and now well, I have to say ionization haven't started yet in this object. The nebula is the optical images I will show later are reflection nebula. So we are seeing the beginning of the protoplanetary nebula phase. Well, this is another thing we can do is so we can analyze the dust properties of this object. This is an ISO spectra, and we see it's a quite complex structure. Well, we don't see here very well because the scale, the region between 3 and 10 microns, but we see some pH structure. But what is important is that we can fit two black bodies, one with a temperature of 273 and another cooler, 130. And what is really interesting is all this emission over the black body, which correspond, I mean, this is a logarithm, but this goes from 18 to 45 microns and corresponds with features at 21, 26, and 30 microns. I'm going to speak just very fast about the dust temperature. We use an emissivity of 1, which corresponds with hydrogenated amorphous carbon grains, HHCs. So we derive those two black bodies. And the warm component dominates the N1 filter, while the cooler component dominates the N11.9 filter. And of course, it's these strong features. Those features, several authors associate with several solid-state compounds, titanium carbide, silicon carbide for the 21 micron feature. Also, it's big claims of fullerenes and nanodiamonds, I include here. And the 30 micron feature is associated with magnesium sulfide. So, of course, 30 micron we can observe with CanariCam, but this, the 21 micron, should be very promising wavelength range to try to observe with CanariCam if the water vapor allow us. So, as I think Jim was saying this morning, it's very important just to schedule use of CanariCam that we can use this window, because this is very important for solid state work. Well, this is an image superimposed on the HST. The HST was taken in the 606 nanometer filter. And we can see there are several outflows at PA 34, 54, 84, and 124. And the torus is aligned perpendicular to this main lobe here at 84 microns. So we pretty much see that the torus makes the collimated, but only of one lobe, not all the lobes. So if we look at the H2 image from HST, this is the H2, the grayscale, and the contours in the 8. I think this is the, well, I'm not sure which filter. I think this is 8.5 microns. We see the H2 is concentrated on the walls, but just on this lobe of one lobe at 84 degrees. So, just to finish, we see that the H2 emission corresponds with the interaction of the fast wind from the central star with the slowing AGB wind, and but this is only happen in one lobe. So this make us think that multiple outflows occurs at different epochs, and probably the other lobes have much cooler dust grains, only detectable in the optical because of scattering properties. So just to finish, what T-Rex, of course, will have much better spatial resolution. Of course, we will go much deeper. I mean, this is just an exceptional example, very bright object in 10 microns, but not all of these protoplanetary nebula are so strong. So our idea is to increase the sample and, of course, try to get better resolution images and deeper images. And, of course, also it will be very useful to use the spectra. We took some spectra from this object, but turned to be not really competitive with ISO. So well, we never use those spectra. So we expect that T-Rex will surpass much better than ISO. So, sorry. Yeah, I'm confused. CanariCam. Yeah. Okay.
Actually, you started late, so you had more time.
Yeah, it's okay.
Are there any questions for Arturo?
When you said that the spectra were not competitive with ISO, is because of the resolution or the sensitivity?
Both. I mean, the sensitivity was more or less similar, and the resolution also. I think our spectra was 150 or something like that, and ISO was something. ISO was around 100. So we really need both more sensitivity and more resolution. And CanariCam will have that.
Arturo, I'm a bit surprised by the dynamical age you derived for the torus because it's so short. I mean, 190 years. Is that a typical time scale? I mean, what's the duration of that phase? Or is that just a very lucky hit?
Well, as I said, it's hard to talk about typical because there are very few protoplanetary nebulae that has been measured. But according to the theory of evolution of stars, this is normal, as I said, because, the number I say about 10,000 is from Myras that has quite uncertainties. I mean, some authors say it may be 1,000 years, or say it's 10,000 years. So we may say it's between 1,000 and 10,000, but nobody knows. and from the observational point of view, there are very, very few objects that have been observed. And also, of course, there are a lot of uncertainties because I'm doing some assumptions here as the distance I mean, I could spend 1 hour explaining you how I do derive this distance, and still there are high uncertainties in this distance because it's not an easy task to derive distances for this kind of objects. And also the assumption that all the CO is in the torus, and there is uniform velocity, so, you know.
Let me ask the question the other way around. Is any characteristic of this planetary, protoplanetary nebula peculiar with respect to the counterparts or companions?
Well, the most peculiar thing is the 21 micron emission. There are only, well, I'm not very sure, but I would say between 10 and 20 objects with this feature, as far as I know. So that's not so many. So that's the main characteristic, peculiar characteristic.
Sort of to ask the question the other way around, how many good candidates are there for the protoplanetaries that you think might be close enough to be able to get good spatial resolution and observable from?
Well, this is a tricky question. So far, have been observed with the HST something like 100, and from those 100, just extended result, extended emission, there are only 20 or something like that. So most of not many. But you know, HST doesn't cover this wavelength range. I mean, HST only goes up to 2.2 microns. So maybe in 10 micron we may see some structure that is not seen on HST. So, but certainly we are talking about at the most 100 targets. But I doubt 100. I would say 10, 20.
I know Jim Huff has actually proposed elsewhere that one look at these things. Well, not necessarily these specific ones, but planetary nebulae polarimetrically. Because one of the nice things about them is the symmetries.
Right, certainly.
Make them an interesting laboratory for beginning to
Yeah.
understand how to interpret polarimetric observations, where you've got some kind of regular structure, and it forms the basis for any more complex regions that we would look at as well.
Yeah.
So these would be really.
Yeah. Well, unfortunately, this is from the south. So. We had to find something from the north. Yeah.
Sorry, just saying we've done a number from UKIRT, kind of near-infrared polarimetry, and look at the scattered flux around these objects.
Yeah. No, certainly. This will be, as you were commenting about magnetic fields. Actually, there is a couple of papers that they have. They claim they have detected the magnetic fields in the central star of planetary nebula with, indirect work. So it's not 100% sure that the magnetic field is present, but there are some work that claim they have detected magnetic fields. And as I said, I mean, magnetic fields is one of the possible polarimetry mechanisms.
Yeah.
Because the real problem here is, of course, we have seen that the torus collimate the outflow, but the key question that haven't been solved is what caused the torus, and nobody has the answer, because you can form the torus with a binary system, common envelope phase, but also with a magnetic field. So combination of magnetic field and rotation, interaction wind. So still nobody have answered that question. Okay, thank you.
Vale.